Here is a positive charge. Around the charge, there is an electric field. How do we know that there is an electric field around the positive charge? We know because of the effect which it has on nearby charges. Let's say we have a charge Q near our positive charge. If there is an electric field nearby, then the charge Q is going to experience a force. And if Q was a positive charge, the force would be directed away from the positive charge. If we can measure a force, then we know there is an electric field produced by the positive charge. And the electric field is given by E equals F over Q. Here is a bar magnet. It has a north and a south pole. How do we know that this magnet produces a magnetic field? We know that this magnet produces a magnetic field because when we put a compass needle near the magnet, a torque is exerted on the compass needle. This compass needle has its north direction pointing towards the top of the page. When I bring the compass needle closer to the magnet, a torque is exerted on that compass needle, and the compass needle changes direction. Now it is pointing towards the right. So magnetic fields exert torques on compass needles. And the torque tends to rotate the compass needle in the direction of the magnetic field. In this example, we can see that the north pole of the compass is pointing towards the south pole of the magnet. Now I will use the compass to map the magnetic field produced by the bar magnet. If I join the vectors, I create the lines of the magnetic field. And the direction of the magnetic field lines is the same as the direction of the red arrows, the direction in which the north pole of the compass pointed. You can see that the magnetic field lines point towards the south pole and away from the north pole. This is a magnetic field sensor. I can use this instrument to determine the magnitude of the magnetic field around the magnet. Right here I'm measuring 2.57 millitesla. If I reverse the direction, I measure negative 2.7 millitesla. So I can also determine the direction of the magnetic field with this instrument. But now I'm just interested in the magnitude of the magnetic field at different points around the bar magnet. You can see that the magnitude of the magnetic field decreases as you get farther away from the magnet. And also, the magnetic field is largest at the poles of the magnet. And from this diagram, you can see that as the density of the field lines increases, the magnitude of the magnetic field increases. Just like we saw for electric fields. We have a greater density of electric field lines, you have a greater magnitude of the electric field. we can continue the magnetic field lines inside the magnet. And you can see that the greatest density of magnetic field lines is within the magnet. So that's where the greatest magnetic field strength is going to be. So magnetic field lines, as you can see, form loops. They don't end on a north pole or a south pole. This is a difference between electricity and magnetism. Electric field lines always end on positive charges or negative charges. Magnetic field lines don't end on anything. They form continuous loops. That is because there are no magnetic monopoles. We have electric monopoles, which would be a positive charge or a negative charge. But for magnets, the north and south pole are always together as a pair. That's called a magnetic dipole. Here is a box of chocolates. Unfortunately, there's no chocolates inside the box because I ate them all. But what I have instead is a loop of wire, several loops of wire. And I can connect the wire to a power supply, and current is going to flow in the direction of the arrow. What we want to see here is if a current in a wire will create a magnetic field. With no current running through the wire, the north pole of the compass points to the right. If I now put some current through the wire, now I have 3 amps going through the wire, and the north pole of the compass points down. So the direction of the magnetic field in this case is down. Let's just plot some of these points. Now I'm going to stop at this point because the wire is getting hot and I'm starting to see some smoke. I'll join those red arrows together, and this is what the magnetic field line of that current loop looks like. And if we continue this on, we'd have another one over here. And we can put on the directions. It's direction of the red arrow. This distribution of magnetic field lines is similar to the distribution of magnetic field lines for the bar magnet. This loop of wire, when a current runs through it, is a magnetic dipole. Let's measure the magnetic field produced by this current loop. I'll take out the magnetic field detector. I'll give it 3 amps of current. Over here we have 0.4 millitesla. Over here, 0.02 millitesla. Over here, 0.002. 0.048. 0.010. 0.051. You can see here that the magnetic field is greater at the center of the current loop. We have 0.4 millitesla. And as we go away from the center of the current loop, the magnetic field decreases on both sides. Also notice, where we have the greatest concentration of magnetic field lines, we have a larger value of the magnetic field. As I said, when you have a magnet in a magnetic field, that magnetic field will exert a torque on the magnet. That's how you can make an electric motor. Here is an electric motor which I made. It consists of a current loop which is free to rotate. Have a power source, a battery. Current is going to flow through along here, through the current loop, and back to the negative terminal of the battery. We also need a magnet. Here's a magnet. I'll put it right there. This current loop has a magnetic field which points to the left or to the right. I need to just start this. There it goes. Take the magnet away, of course it stops. I can put the north pole of the magnet here and start it going. If I switch to the south pole, it now goes in the other direction. Here is a solenoid. It consists of many loops of wire around a cylinder. It is hollow inside. I'll connect up the solenoid to the power supply. I'm going to run 2 amps of current through the solenoid. Watch what happens with the compass needle when I turn on the current. I now have 2 amps of current, and the compass needle went from the north pointing to the right to pointing to the left. If I move the compass needle around the solenoid, the direction of the compass needle is going to change because the magnetic field of the solenoid is going to apply a torque to the compass needle. Over here, the compass needle is pointing towards the right. When I come to the other end of the solenoid, the compass needle points towards the left. In fact, inside the solenoid, it's always pointing to the left. Let's plot the magnetic field lines. So we'll just plot the direction of the compass needle. It's going this way, this way, now let's join up the red vectors to draw the magnetic field lines of the solenoid. And the magnetic field lines also go right inside the solenoid. This is similar to the magnetic field lines of the bar magnet and of the loop of wire. Now let's measure the strength of the magnetic field inside the solenoid. I'm now running 2 amps through the solenoid, and I'm going to use this magnetic force sensor to measure the strength of the magnetic field. Right at the edge of the solenoid, I've got 3.0 millitesla. As I come in, it increases. At the very center of the solenoid, I've got 5.6 millitesla. If I go to the right, or to the left, or I go up, or I go down, there's not much change in the magnetic field. It's constant throughout the interior of the solenoid, as long as I'm in the center of the solenoid. If I come to the outside of the solenoid, I've got a magnetic field strength of 0.5 millitesla. It's about 10 times smaller on the outside of the solenoid than on the inside. If I move farther away, the magnetic field drops even more. So we conclude here that the magnetic field is uniform near the center and inside the solenoid, and it drops by 10 times when you get to the outside of the solenoid, and as you move farther away, it gets even smaller. Here is a piece of steel. I'm going to see what happens if I put this steel inside the solenoid. There's a force on this piece of steel. Look at this. It gets pulled right into the solenoid.